My name's Chris Orwa. Currently I work for the Safaricom Innovation Department as a data scientist. I blog sometimes. This, a few people might know me because of online activity. I also write for Daily Nation now. I have done so many hackathons. I was like, okay, the best hackathon that I ever did was sponsored by Al Jazeera to build tools for better news. My project was to create a tool that would generate a different headline for everyone, depending on your emotions, who you were, and you go through your Twitter feed, and we generate a different headline so that you see different things for kind of people. So I quite enjoyed it. So I've done so many of them, but I kind of started running away from hackathons because of work and etc. But I've been doing it for about, I'd say 7 to 8 years, because I started doing data mining around 2010 when I finished university. Had a startup to analyze data for companies, worked there for 2 years. Then I got a job at iHub as a data scientist. I was doing a lot of social media predictive works at iHub, predicting where violence will happen during election and etc. And I stayed at iHub for about 3.5 years, and then I moved to a company called Brave Venture Labs. It's an AI HR company that's predicting human performance at work and finding people who match opportunities. I stayed there for about 1.5 years, and then last year I moved to Safaricom. Okay, so I wanted to show you a few things that have been done before that will probably help in the whatever you do. One of the things that I noticed and experienced as well as read about is when you're provided with a data set, you shoot straight into the data set and start running your algorithms and trying to ensure that your prediction is as accurate as possible. Rarely do people take time to sit back and start understanding the problem from a different perspective, which if you done some philosophical thinking, they call it inductive reasoning and deductive reasoning. So inductive, you look at the data, make some conclusion. Deductive, you start thinking about what kind of transport problems do we have in Kenya? What of different modes of transport do we have? Do we have more people on one type of transport than another? And having those, let me call them bigger, overarching ideas helps you to even think about how you're going to solve the problem before straight diving into the problem. And I think data science is also really taught as that algorithmic part where you write the code for that. But I think it's a bit broader than that. So who has seen this map before? No one. Oh, good, good. If you've never seen this map before, there's a research, I think it was MIT-sponsored research project. They had a project known as Digital Matatus. And they went throughout Nairobi, mapping different start and stop points. So where you take your matatu and where you terminate your matatus, and built this very nice map to show different routes that people take in Nairobi. They also timed what time they were taking through different spots. They generated a very nice data set in that case. And the end of the project was to generate data to show mapping and different routes for matatus only in Nairobi. So one of the friends that I knew decided like, hey, this is a very nice data set. We could actually learn something from here. Before I go ahead, which stage do you think is the most, there's a lot of, which stage has the most traffic in Nairobi? Kencom? Railways, Koja, OTC. What he did, he created a network map which shows, so each node represents a stage. And then the size of the node looks at how many matatus or how many routes pass through that particular node for that kind of place. So after mapping all the matatus destinations and end points and mapping which stages they pass through, the node with the largest node shows that there's so many matatus passing through that particular node, which is actually Tesun Ajib on Haile Selassie Avenue, because it handles traffic from Mombasa Road, from Ngong Road, and it has the highest traffic point for matatus passing through. So possibly something that we'd never know, assuming that railways is the largest and bus station is the largest. So how big was the data set? From what I know, they were taking each, they had researchers sitting in certain roads, and you pick a matatu from point A to point B, and on this sheet here, this lists the extent of which routes they took. So this has names like 111 to Ngong, 48 to Dagoretti, 2 to Believe Karen, etc. So this section tells you the extent of how large the data set was. So the good thing with what this tells me, I already now, even before I jump into the data set, I already have a prior or some information that I know about traffic in Nairobi. If you have an Uber that's about to pass that section, you're very sure it's going to take a longer time to pass through that particular section, plus other sections. And if I was doing some traffic modeling of sorts, I could decide to use these points as have weights on them. So if I'm going to follow a certain route, I could use the size of the node as weights to apply on the time that will be taken for you to take from one point to another. So that's one way that you could think about solving a traffic problem or a useful data set. This data set is actually open source. If you go to the website digitalmetatus.com, there's a section you can go get that data set. And which is equally also important, when you're building features to predict, you don't necessarily have to limit yourself with what has been provided into the competition. If you can find another data set to include and extract more features that would have more predictive power, then by all means, you should use it. So I don't know that sometimes you have extra information that you don't know, or instead of including the information, you use the knowledge that I already know one or two things about traffic. And in statistics, there are two ways of reasoning. So there's the frequentist and the Bayesian reasoning. Anyone has like fun about that? So they generally argue that a frequentist, for them to know an answer, they always have to do they have to count. So if I ask how many people are in this room, then I say like, okay, you can just go around and count. A Bayesian person would say like, what do I already know about this room? Help me count. So you go into a situation already knowing something about that situation, and you don't have to count every time. So you utilize information that you know to help you start analyzing or thinking about how you're going to analyze the problem, instead of having to do counts or experiments or write code all the time for those particular aspects for that. I want to tell a story. People don't like war, but wars have very good stories to tell. Actually, a lot of technology that we enjoy today came out of World War II. Rockets to space, laser on your CD, radio frequencies, and other improvements in technology came through the war. So in 1939, as you know, or most of you know, the most evil person on earth, Adolf Hitler, unleashed his mighty army to go and conquer Europe. So at that point, they had like the best fighting technique. It was known as blitzkrieg. It is a innovative way of fighting using tanks. So they went and conquered France, and they're on their way to conquer the Soviet Union. So when they got to the Soviet Union, the Russians had discovered that the main strategy about the Germans was built around tanks. So they built better tanks. So when they went there, they were almost repulsed back. So Hitler decided, like, you know what? We're going to have to build a better tank. So he went and collected all manufacturers of vehicles and said, like, hey, I need the best tank that could be built. So Porsche, as you know it today, plus other industries, built this tank. It was known as the Tiger I tank. It was the most feared tank in World War II for two things. It had very good armor, and its gun was very accurate and carried a lot of punch for it. So anytime the Allied soldiers would meet this tank, either they used to take 4 tanks to hunt one of these tanks. If you've watched the movie Fury, you would know it's true. So the Allies got overwhelmed about this tank. They're like, we have to kill these tanks. You have to kill production. Otherwise, this war is going to extend. So because they used to have a technique, they would take 3 tanks, put it on front like ducks. So while this gunner is trying to shoot those 3 tanks, a 3rd tank will come behind and then blow it up because this tank never had armor from behind. So they would lose 3 tanks to kill one of these tanks. So they said, like, you know what? We have to do the mathematics. How many tanks do we need to clear the stock that the Germans have? They never knew how many tanks Germany was making. So they formulated a mathematical problem known as the German tank problem. Can you predict how many tanks the Germans are making every month? So they gave this task to an economist who used his knowledge about efficiencies in the market and how production works. He could not crack it yet. So they went to the pre-war records to figure out how many factories they have, what's their capacity, and etc. And then they combined that by confession from captured soldiers. They could still not crack it. Then one day, this economist went to London and said, like, wait a minute. These tanks have serial numbers. Like, this one is 211. And like, these serial numbers must mean something, right? So he decided to figure out that if they're producing these tanks in series and they're giving them serial numbers, a higher serial number must be able to indicate that this is the level they are at production for those particular tanks. So anytime a tank was captured or was left in the field, he asked the field soldiers to send him photographs of the numbers of these tanks. And then he developed a formula which he used to say that, hey, if M is the largest serial I've observed, and I have K of such numbers, what is the chance that that number I've observed is the highest in the production series in that? And this is, in statistics, became a very important tool to be used for you to predict when you have less information in that case. Became a very, you can read about it, it's called the German tank problem. So ever since then, this formula has been very useful for people. So example, iPhone normally limits, they don't tell how many iPhones they produce. So one guy went to the web and asked people to send photos of the serial numbers on their phones. And then using this formula, he's able to calculate how many iPhones are being made by Apple every month for that. And being who I am with all my craziness, I was like, I have to apply this somewhere. This story is just too good to just let it slide. So I went and I went to the CBD, and I realized certain bus companies, they have, of course, their number plates, but they also have a number written next, like a fleet number, or like this is City Hopper, 3 something something. Then I was like, you know what? I could know how many City Hoppers exist. Umoina. Yeah. So I collected data for different bus companies using the same formula that I have. As like, I want to predict the certain level of certainty that, or probability that they have the highest number. And boop, turns out KBS has the largest fleet in Nairobi, followed by City Hopper, City Shuttle, and yeah. So from that observation, I could make an inference. Now I know the stages that have the most traffic. I know the bus companies with the most number of matatus in Nairobi. Now, my information about traffic in Nairobi is getting clearer, especially from a public service perspective. Okay? Great. So, I did put in some code there, but I'll skip it for now, just to on how to simulate for the German tank problem for that. And other things I was looking at, how your fleet is aging, how long you're replacing your fleet. Let's get into a way of thinking that would help us come closer to predicting better on our current competition, and some statistical ideas that we may have. So I've already talked about Bayesian way of thinking. It's generally knowing how to be, I'm trying to find a much more, it's like being smart. If you ask a question, go with some smartness into the question. From a statistical and a mathematical perspective, this way of thinking has an interpretation. I know some of you don't like maths, but I'll just explain it. It says, P is for probability. What's the probability of B, assuming B is an event, what's the probability of B happening given that A has happened, right? And then it has how to implement that. It's normally known as conditional probability. But just, if you don't care about the math, just care about the concept. That what's the probability of one thing happening if another has happened before? Yeah. What's the probability of you ending up in CBD if you passed Junction? What's the probability of you ending up in Westlands if you pass somewhere else, right? So it's a way of doing math instead of, you look at things that have happened before, what happened before them, and calculate the probability of something happening when something else has happened before, right? What's the chance of it raining if the clouds are dark, etc. Okay? Then there's a second part connected to it, which is known as a Bayesian network, which I love a lot. It tells you, so you have your data and your variables, and you're trying to find which variables have what you call conditional probability. And in this case, you're inferring a causal relationship that one thing causes another. So if you think about this, like, what are the things that causes cancer? There's always a high probability that a smoker has lung cancer or has tuberculosis, and you can see the direction for that. You see that the network that we had before was just looking at routes and where cars are passing. So it lacks some intelligence or some mathematics to it that makes the information more useful and have predictive information. But Bayesian networks are always be calculating what are the chances that you have tuberculosis given that you're a smoker. If the probability is high, then I infer that one thing causes another. And if you think about your predictive model, you might have different functionality, different variables, and you could say, what's the probability of a bus being half full given that it originated from this place, right? Or what's the chances of selling 50 tickets given that the bus was half full, came from this town, and originated from this town or made a stop at this particular town. So you can build all those connections using Bayesian inference. I will not bore you with this. It's just a way of getting the actual probabilities. There's an algorithm known as Bayesian belief propagation algorithm. So once you've built the network and you want to know the exact probabilities, you just run the algorithm and it returns you back the probabilities of the probability of this and this happening is this. Probability of this, this, and this happening, given this has happened, and it can be a very long chain, right? So we have two problems, the Uber one and the Mobi ticket one. When I look at Uber, I think about a grid system. That's how my mind has been fixed. And then, so this x-axis becomes our latitude, and y becomes our longitude. And then let's place the map of Nairobi inside here, okay? And then let's divide each section into a grid. So we can name these grids the way we like, grid 1, grid 2, grid 3, and etc. And then, now then we have the Uber traffic data that sits on top of this, okay? Then in my conceptual mind, I'll think like, okay, there's a trip that originated from here, went to this place, and then finally terminated here, right? So in a way, to make it feel more conceptualized, this is the data set I'll create. So each of those grids, I give those grids a name that maybe represents the popular feature for that particular place or whatever makes it easy to understand. Then each grid has an X and Y just for understanding or whatever that there is. And then in here, I would place how long it took the Uber driver, assume I have that minute data, how long you took in that particular grid, okay? And assuming, did I put tickets here? Okay, I should have put destination actually. So let's go back. Of all these grids, what's the probability of you being here or landing here or taking 10 minutes here, assuming that's your target variable, given that you've been here, 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 and here? Make sense? Yeah, so I would think of an unsupervised lining approach. If I run a Bayesian network here, each of these would be a grid, okay? And they tell me the probability that I'll leave this grid and go to this grid is this much. The probability I'll leave this grid and go to another grid is this much. The probability of me moving from this grid to this grid is almost 0, right? So I'm modeling my problem in a way that I can understand or give more useful feedback. So ideally, Who wants to take a guess, if we use the grid example, what this would indicate? You'll have highways, of course, because people will follow highways when they're going direction. But also, what I'm able to detect is the panya routes that the Uber drivers use or prefer using in that scenario. Because if this is a destination and this is the origin point, I would see that maybe this is the most popular route. This is an alternative route for that. And I can assign weights, like what's the time for this route, what's the time for this other route. But it tells me the probability of a driver leaving this destination and landing here is this much. The driver from this destination is here. So it maps for me different alternatives that drivers could probably use. What I was thinking about is, how do you make a prediction, okay? The prediction can include the driver's preferences. The prediction might not include the driver's preferences. Remember, you're trying to predict traffic. The drivers themselves contribute also to traffic by the choice of routes they use. So I've never looked at Uber data. I don't know which routes drivers prefer, right? So I want to know which routes drivers prefer. So by mapping different points and calculate the probability of a driver moving from one point to another, I eventually build a route for myself. And I can visualize that route using the Bayesian network, and then I make a conclusion that this is actually the route they follow. This is the time that it takes to follow. So if here, which certain tickets, so this is, I'd call it like a target variable. So let's assume you don't have this. So each row represents a trip. Okay? So this is trip 1, trip 2, trip 3, up to trip 60. Then these columns represents the grids that the driver used, right? And I'm calculating, on average, what's the probability of a driver moving from this grid to another grid, okay? So I have the general network. But once I create a target variable, which is what am I interested in predicting? Is it the time? Is it cost? Is it happiness? Let's assume this is happiness. I could say drivers who hop from this, this, and this, and this, and this have a less happiness. Drivers who go bum, 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 bum have another happiness. So Bayesian networks, Bayesian inferences, and conditional probability tells you what preconditions need to exist for certain thing to happen. We can decide what needs to happen on this column, and we just calculate the chain probability that will end up in that particular column. Okay? Something that I just read, again, I know people hate a lot of mathematics, but this does not exist. You have to write the code yourself. It's known as some people call it Braille, but I prefer Brie, which is the French way. I think that's the correct spelling for it. So this FT is a forecast that you make, okay? OT is the outcome that was there. So let's say I calculated my probability. I said, like, the probability of a driver jumping from this grid to this grid is high. So I'd say I'd give that probability 0.6 probability or 0.7. That's what I've forecasted. But then the driver does not end up. So if the driver ends up at that grid, I give it a 1. If he doesn't end up at that grid, I give it a 0. So the difference between what I forecasted and what the actual outcome was, so if my forecast was probabilities, the combined probability is 0.6, and the outcome was 1, the difference is minus 0.4. I square that. Then if I do that for all my calculation, I get what you call a Brie score, which is how good am I at making prediction? How am I making better prediction? One of the things why I thought this is very important when you're normally doing predictions, you normally build a model and then use another metric for prediction. But what I thought is important, how about you include this while you're calculating for that? I've split my data into training and test set, and I'm saying I have an idea which says that if you hop from this point and this point, this is how you'll end up. If you don't end up, or if this score becomes extremely low, which means I'm not performing well, what do I need to change about my model? This should be an easy code to write. It's just a for loop, and how many predictions you've made, what are the outcomes, and your predictions, and then it's squared for that. So this is another means for telling how accurate you are. I read about it in, there's some guys who are trying to predict world events. If an event happens, it's a 1. If it doesn't event, it's a 0. And you're supposed to assign a probability of that event happening, right? So you could assign that probability using a conditional probability for that. And in R, there are so many packages that you could use to calculate probabilities and conditional probabilities in that case.